Okay, so in this lecture, we're going to look at the Fischer reaction or the Fischer esterification. So I like to think about this as the reaction of carboxylic acids with stronger acids in the presence of alcohol. Just some ROH group. Okay, so what we do in this case is we take a carboxylic acid and we react it with an alcohol, and we have this stronger acid that's used as a catalyst, which I'm just going to denote as H+, and that is going to facilitate the conversion. I'm going to call this alcohol R prime. Okay, that's going to facilitate the transformation where the carboxylic acid turns into an ester. So we now have an ester functional group. And if we balance the reaction, we have water that's being formed. Turns out that this is an equilibrium process that follows Le Chatelier's principle. Follows Le Chatelier's principle, whereby if you have more alcohol, this is going to lead to more ester. And if you have more water, that's going to give to more of the carboxylic acid. Okay, so that's kind of an important point, because it turns out that carboxylic acids smell, I mean, they're not as bad as thiols. Like, they don't smell super terrible, but esters, wow, esters smell good. And this reaction is the focus of the banana oil lab, or the Fischer esterification lab, as the name would suggest. And that's kind of a flavors and fragrances lab, where you're converting something that smells terrible into something that smells good. It doesn't really smell like, it just smells kind of bitter, and it's annoying to smell carboxylic acids. So some of the one of the esters that I really like to make for that lab smells like artificial bananas. It's really like a weird brain thing. Like, that doesn't smell. If you sit back and think, it's like, what do bananas even smell like? But if you smell these, they smell exactly like banana Laffy Taffy, the chemical that results from this transformation. So you can make these things smell like all sort of interesting things that are pleasant to the brain, which is great, because it's nice to not smell terrible things and to smell good things instead. So here's the issue. People got some that made some that they were like, okay, that's pleasant, not too fruity, whatever. Let's dab that in the underarms and the areas of the body that start to smell towards the end of the day. It's kind of like a deodorant or cologne, I guess, back in the day. So the unfortunate thing is, as this equilibrium suggests with Le Chatelier's principle, if you take your ester that's pure and you sprinkle it on it, put it in an environment that produces a lot of water, that's acidic, like sweat, and you add some heat to this, you can actually drive the reaction in reverse. And you might start off with a little bit of cologne that smells nice, but then by the end of the day, you've sort of like snowballed the body odor because you start to have these really stinky carboxylic acids. Okay. Anyway, let's go through the mechanism of this. Black pen here. So the mechanism is, I'm going to use this term quite a bit in the in this module, and that's the addition elimination reaction. So we're going to be talking about this a lot. This is kind of a fun part about this last unit, is there's kind of a common mechanistic theme, sort of like what we saw with the electrophilic aromatic substitution reaction. Well, a lot of like what we saw with that, where one kind of overarching mechanism governs all of the mechanisms, which is people like. It's a little bit easier to understand and follow and predict. But anyway, okay, so what we have here is a carboxylic acid, and this is going to engage a strong acid using one of the pairs of electrons on the carbonyl oxygen, not the oxygen that's drawn with a single bond, to get us this species. Then you could put the double bond anywhere. I mean, if you really want to, instead of the lone pair, you could consider a resonance structure doing the attacking. That's also fine. Gets you to the same place, because this is just a resonance structure, as though we put the positive charge on the carbon between the two oxygen atoms. Okay, so it's this latter resonance structure that allows us to see that the alcohol is going to come in. So notice that we added the alcohol at the outset of the reaction, but it doesn't come in until after what happened first? The acid reacts first. H plus reacts first. It's just a subatomic particle. So the acid reactions happen first. So that strong acid goes on first. Then the alcohol attacks. Turns out the alcohol is not a strong enough nucleophile, and the carboxylic acid is not a good enough electrophile unless that acid is present and has protonated the carbonyl oxygen on that carboxylic acid. Okay, so the oxygen from the alcohol is going to attack using one of its lone pairs. This is going to feel a lot like a hemiacetal mechanism, and that's good. That's good if you recognize that. Now, at this point, what we have to realize is that we need to push off an H2O. So we have to generate an H2O leaving group, okay? So what I'm going to do is let the hydrogen drop off of the molecule to get to a neutral intermediate. When I do that, I lose H+. Now I can pick either of the OHs to let their lone pairs engage the H+. That's going to generate my good water leaving group. Now you have a few options here. You could lose that water to get to a positive charge that's between two oxygens. That's a highly stabilized positive charge, because we could draw a resonance. We could draw a resonance from either of the lone pair oxygens. But instead, what I'm going to do is I'm just going to let the H+ fall off, neutralize that positive charge, regenerate the carbonyl. And if we look, I'm sorry, I should have, well, okay, I'm going to leave the R groups. The R groups can be different, but let's not worry about that right now. Okay, the ester can have different things on either side of it. Okay, after we lose that H+, we regenerate the H+ that we need to catalyze the reaction. Again, this is another example where the acid has been fully consumed and we've regenerated it, but the H+ we get at the end of the reaction is not the same as the one we started with. Remembering our definition of a catalyst, a more precise definition is one where the catalytic agent is both consumed and regenerated, as is the case, which is true for all catalysts. Okay, so we've lost water at this stage. I should just mention that. So what we did was we drove off water and we regenerated the H+ to make our ester. It looks like a lengthy mechanism, but it follows the trend that we're going to see with this module, where we first start with an addition, and then we finish with an elimination, where we add something and then eliminate something. Add the nucleophile, eliminate the leaving group. Add the nucleophile, eliminate the leaving group, addition, elimination. We're going to see this over and over again. And so I like to show this. Maybe this is a little bit too early to show this mechanism. It's a little bit complicated, that sort of thing, but we try to do an experiment like this in lab, and it really sets the stage for all of the addition elimination reactions we're going to see going forward. But just a reminder, we can do this reaction in reverse. If we add a bunch of water to an ester under acidic conditions, the mechanism is entirely in reverse every step of the way. Okay, well, at that point, that's all I want to say about the Fischer esterification. It's a super versatile reaction. Every time I've tried to use it, if I'm not doing something that's too sterically hindered on the alcohol, I can make most any ester that I want. And similarly, I can hydrolyze or convert any ester I want to a carboxylic acid for the most part. So it's a really nice reaction to do, pretty easy. Just mix the alcohol, add a little bit of acid to the alcohol carboxylic acid, heat it up, watch it form. Sometimes you need to figure out a way to remove the water. But anyway, that's all I'll say about this reaction. So we'll continue onwards into methods for synthesizing carboxylic acids coming up next.